I'm sorry, can't hear you.
Can you hear me now?
Yes, we can. Thank you.
Okay, so sorry for this. Good morning, everybody. Sorry for this technical problem. Today we need to talk about a very important library called sklearn. We use it in machine learning for building models and testing models. So we will talk first about sklearn, and after that we will talk about a very famous problem called iris classification in sklearn, or iris classification. It's a very famous problem in computer science or in machine learning. They use it for training models and testing models. We will try to solve it as a binary classification problem, and later on we will solve it as a multi-class classification problem, because this problem has 3 classes. We need also to learn how to plot the decision boundary. So when we classify a problem like iris classification, if it is binary classification, we need to know how can we plot the decision boundary, which is a line which will separate 2 classes into 2 distinct, 2 different classes, for example. To train your model, there is something called the validation protocol. And to do this, we need to learn how to split our data into training and testing. It's very, very important, because you cannot use your whole data set for training your model. It's very important to divide your data into one part for training and one part for testing. There are 2 techniques, one called hold-out validations and the cross-validation, for example. So we need to talk about it. We studied a perceptron. So we need also to use, how can we use a perceptron for multi-class classification? So there is one famous technique called one versus rest approach. We need to use this technique for solving multi-class classification, because from lecture 2, we know that a perceptron can be used only for binary classification problem. But if we need to use it for solving a multi-class classification problem, we need to use a simple technique called one versus rest, or OVR. We will talk about some different versions of a perceptron. So for example, there is something called adaptive linear unit. It's the same as a perceptron, but with linear activation function. So we need to know what is this model, adaptive linear unit, and also a logistic regression classifier. So what is the difference between logistic regression classifier, adaptive linear unit, and a perceptron? In fact, the difference, it's the same structure, but the difference is in selecting different activation function. We need to use logistic regression for iris dataset. So how can we use logistic regression to classify this problem, for example? Also for data sets, there are some data which are separable and inseparable. When it is separable, we will be able to classify it using a linear perceptron, for example. When it is inseparable, it's impossible, because inseparable data sets, it means it requires more than one line for classifying it. And we cannot get this line using a single perceptron. So in this case, maybe we need to use something more complex, which is a feed-forward neural network. To evaluate your model, if it is classification problem, we need to understand something called the confusion matrix. So we can use this confusion matrix for to evaluate the performance of our model. We use this confusion matrix only for classification problems. But if it is a regression problem, we can use some other evaluation metric, like root mean square error, for example, or any other metric. But confusion matrix, we use it for testing the performance of a classifier. And finally, we will talk about multi-layer neural network, which is, our course called neural network. So we need to build our neural network. So we will use multi-layer perceptron, and this multi-layer perceptron, in fact, it's an extension of a perceptron. So the perceptron, it's a very basic unit. If we need to draw a perceptron, it will be like this one. So the perceptron will be one unit, and it will be connected with some inputs. If we have 3 inputs, it will be like this one. So we have x1, x2, x3, for example, and all inputs are connected with this unit using some weights, omega1, omega2, omega n. So this one, it's a perceptron. If you want to build multi-layer classifier, for example, multi-layer perceptron, it will be just an extension of this one. So we just need to add more units and add more layers. So it will be exactly the same, but just adding more units and more layers. So this one, we call this one MLP, multi-layer perceptron, or some people, they call it feed-forward neural network. Feed-forward neural network. So, so we can use this multi-layer perceptron for solving more complex problems. So if you have a data set which is complex, similar to this inseparable data set, for example, so it will be impossible to solve it using a perceptron. So in this case, we need to use multi-layer perceptron to solve it, because multi-layer perceptron, has more parameters, and it will has much higher capacity for solving more complex problems and the more complex mapping between inputs and outputs. We need to know how to implement MLP classifier in sklearn. It's very, very simple. And we need also to understand also how can we implement MLP classifier in Keras. So in fact, we will talk about two libraries, one called sklearn, which is very nice and very beautiful, and also something called Keras. Keras is very, very important. We can use it also for building the same classifier. But usually Keras is used for more deep learning models. So deep learning models can be implemented in Keras, for example. So, but it's the same also if you want to use multi-layer perceptron in Keras, it should be possible to implement it in Keras. So please, if you have any questions, just ask me immediately, please. So scikit-learn, it's a Python machine learning library, which offers fast collection of machine learning algorithms from data processing. We can use it, starting from data processing, when we are collecting raw data, we can use this library for data processing, selecting a model selection, model training, fine-tuning your model, and the model evaluation. So you can do all the pipeline. So because we have a pipeline, in fact, and this pipeline starts by data collection, and after we collecting our data, we need to do some data pre-processing. We need to visualize our data. We need to put our data in the right format for our model. Also, this library has lots of models. So for clustering, for regression, for classification, you can select different types of models. So it will help us to select the best model selection, as you can see here. And for data pre-processing, we have lots of stuff for data pre-processing. We can use feature extraction, for example, normalization, standardization, for example. So data processing, it's a very powerful tool. We can use it for converting our data from its raw format into a format which is suitable for training our model. It has also something called dimensionality reduction. Dimensionality reduction, it's a very important technique because we can use it for to increase efficiency. In fact, we can reduce the dimension of our data, so we can easily visualize it, and we can also increase the performance of our models if we can try to reduce the dimension of our data by removing noise and removing redundant data, for example. So we can just keep the most important data for building our model. So there are lots of techniques for in dimensionality reduction, for example. At least we have something called the principal component analysis, PCA. We can use this principal component analysis to reduce the dimension of our data from its original format into a lower dimensional vector, for example. And in this case, it will be much easier for you to visualize it. So imagine that we have a data set which has 4 input features. It will be very difficult to visualize it in 4-dimensional space. But if we can convert it from 4th or 5th dimension into 3rd dimension, it will be easy to visualize it in 3 dimension, as you can see here. So dimensionality reduction is something very important. Data pre-processing is very, very important because we can use it for feature selection and feature construction. For example, we can select features using this tool. What is the most important feature to use, for example? We can select a model, and we can use this model for classifications, for regression, and for clustering. And I want to tell you that clustering classification and regression, it's supervised. This one is supervised technique. Supervised. But clustering, it's unsupervised. So we have some supervised techniques and unsupervised techniques. If you want to get more details, you can try to Google it, and you can go to this link, for example, to understand more about this toolbox. So I want to explain this IRIS dataset because we will use this dataset, in many places. So I want to explain it. This IRIS dataset, it is used for classification. It's multi-class classification problem. And the input features here, as you can see here, we have 5 columns. The first 4 columns are input features, right? We call it input features. And the 5th column here, this one, it's the labels or labels, right? Or we can call it target feature. This is labels, or we can just say it's target feature. And if you want to use a neural network, for example, for solving this problem or a perceptron, we need to have a model, and this model will be like this one. We will have a model, and this model will have those A, B, C, D inputs. I will call it as it is. So it will be like this one. So we have A, B, C, and D, for example, and we need to use those 4 inputs to try to predict the label, which is a class label, for example, which is E. So we need to build a model like this one. And in this case, we can replace human expertise, because if you have someone who is very clever and he can try to classify those species into 3 types of species, because we have 3 classes here: Iris, Setosa, Virginica, and Versicolor, for example. So we have 3 classes. And we try to do this classification using those features. So we have this petal. You see this one? So this one, it's called the petal. And this one, it has a length and it has a width. So we need to measure the length and the width. And also we have this one, which is called sepal. And this sepal also, it has a length and a width. Using those petal length, and width, and the sepal length and width, we can classify those species into one of those 3 classes. We have 3 classes. So the idea here is to collect a data and try to label this data. And after that, you can build a model which can automatically classify those species into Setosa, Virginica, and Versicolor, into one of those 3 classes. So in this case, we will try to assist the people, for example, because maybe you don't have expertise to classify those species. So instead of hiring someone to do this classification for you, for example, or if you want to automate it using computer vision system, for example, to classify, in this case, we can build a model which should perform at the level of human intelligence. If you have someone who is clever for solving this problem, we can just ask him to collect a large data set, and he will label those species. So he will look into sepal length, sepal width, and the petal length and the petal width, and he will say, okay, this one is Setosa. Correct, and also he will collect a data set which will cover all different species or classes. Here we have 3 classes, and after that we can use this data set for training a model. And this model should be performed at the level of human intelligence, and it should be used for doing those classification automatically. So now we need to try to load this data set, for example, and try to use a perceptron for classifying this one. If you will use a perceptron, you can use 2 inputs, 3 inputs, 4 inputs. It doesn't matter, in fact, correct? But it's just I will select only 2 inputs because I need to plot it in 2-dimensional space, right? So if I will select A and B, for example, so I will have one axis called A, one input called A, one input called B, for example, and I will plot. So I will select, for example, A and B as my inputs. I will ignore C and D, and I will plot my classes against A and B. So it will be something like this one. So maybe one class will be like this, and the other class will be like this. So I will select the first, and also I will select the first 100 points, because in this data set, each 50 points corresponds to one class. So if you want to convert this problem into binary classification problem, we need to select the first 100 points, only the first 100 points, because the first 100 points corresponds to 2 classes. So So after doing this, we will train a model, and this model should be able to plot a decision line, right? And this decision line will be my model. It will be my classifier. So this decision line, it will be my classifier. And we will say that all data points which are located above it will be classified into, for example, Setosa. And all data points which are located below it, it will correspond to the other class. So we will have two classes, class 1 and class 2. And in this case, we will be able to build a classifier to classify this problem. So we need to go for the implementation. So I want to share the link with you first. Okay, I will share the link with you. So you can try to open it in your computer and try to, it's in the chat now, please. So try to open the link and try to play with it. And after that, we will discuss. So you will have 5 minutes to open this link and try to. So I will share it my screen with you. So I opened this link here, right? So please open this link and just try to see, the components. So first here we try to import those libraries. NumPy, for example, sklearn. I need to import datasets from sklearn because if I need to upload iris dataset, I need to get it from datasets.sklearn, right? So from sklearn import datasets. This one we will import this matplotlib. It's for plotting. And I need to select a model. So I will select a perceptron from linear model. And standard scalar, it's just a data preprocessing or normalization standard scalar. I will get it from sklearn.preprocessing. After that, I will load my data. So I need to run that part. And in the second part here, I try to load my data set. And as you can see, I will load the whole data set as it is, in fact. So I will load my whole data set as it is, and I will try to plot it. So as you can see here, we have 3 classes. Those are the labels of those classes, class 0, class 1, and class 2. And I just try to plot it I try to plot it in 2-dimensional space, right? So I will select to plot the data against the first feature and the second feature. So it's A and B in the table, right? So I will plot it against sepal length and sepal width. And as you can see here in this graph, we have 3 classes. Those classes called Setosa, Versicolor, Virginica, and then we will plot it. We will plot the 3 classes using 3 different colors. So we have this one, it's Setosa, and we have also those 2 classes which are overlapped together, Versicolor and Virginica. So I would like to give you 5 minutes to look into the code first, and after that we can discuss it. Is it okay? So 4 minutes.
Yes, okay.
Yeah, please. Thanks. Hello back. So did you have a chance to look into the code? So now we
Yes.
want, okay, very good. So is it easy to understand?
Yes, it's understandable.
Okay, very good. So we have those three classes, and we try to plot the data set. I don't know, we have here only labels. We should get the labels, all labels. We should get all labels here, but okay, so we are plotting the whole data set against two features, which is feature number 0 and feature number 1, which is petal length and petal width, as you can see here. We have three classes, as you can see. And as you can see here, if we need to plot, if we need to classify this one, we have three classes. So if we will use a perceptron, the perceptron will generate only one line. And I need to draw a line. Yes. If we need to use a perceptron, the perceptron will generate only one line. So I will draw this line. So maybe we need to get a line like this one, correct? As you can see. So do you see this line? We can use this line for, because one perceptron, it will generate only one line. So all data points which are classified above the line will be classified into Setosa, and all other points will be classified as maybe versicolor and virginica. So we have three classes. If we need to classify this problem using a perceptron, it will be impossible, correct? Because perceptron is used only for binary classification problems, right? It is used only for binary classification problems. So it's a problem here. We need to get another perceptron because we have three classes. So in this case, in fact, today we will use a technique called one versus rest. If you have three classes, you have, for example, this is class number 0, maybe this blue one or green one, it will be class number 2. The yellow one, it will be maybe class number 3, for example. So in this case, in fact, we can classify this problem using three perceptrons. And we will use a technique called one versus rest. But if you want to use only one perceptron, so in this case, we need to make this problem more simple. We need to just select two classes. So the problem is binary classification problem. And as you can see here, if you look into our data here, sorry, need to clean. Okay. If you can look into my data set here, you can see that the first 50 data points are class number, this one. One more time, we need to annotate one more time. So as you can see here, I mean the first 50 points, do you see those first 50 points? They corresponds to one class. We call it class number 0, which is Setosa. This is class number 0, which is Setosa. The label, which is 1, it's another class, correct? This is class number 1, which corresponds to versicolor. And number 2, class number 2, it's another one, which is virginica. So as you can see here, we have three classes. So if you want to solve this problem using a perceptron, so in this case, we need to select only two classes. So for example, we can select the first two classes, which are Setosa and versicolor. And in this case, we will use only one perceptron for classifying this problem. But if you want to classify it as a multi-class classification using the three classes, so in this case, we need to use maybe MLP, multi-layer perceptron, because this problem is complex, or maybe we can use three perceptrons using this one versus rest. If I want to plot it for this one versus rest, it will look like this one. I will have one perceptron to classify class 0. It will classify 0 against the rest. And I need to have another perceptron to classify class 1 against the rest. And I need to have a third one which will classify the second versus the rest. And the inputs will be how many inputs we have. Maybe we have here 4 inputs. right? And because we have here A, B, C, and D, so it will be A, B, C, and D, and we need to make those connections to everyone, right? So it will be like this one. So if you want, it will be like this one. So in this case, we can use one perceptron for each one. For each class, we need one perceptron. So we call this one versus rest. And as you can see here, this one, in fact, it looks like a multi-layer perceptron. It's one layer, it's not multi-layer, but it's one layer with multiple perceptrons, correct? You can make it multi-layer perceptron easily by adding by adding another layer, an output layer, and so on. So we will clean this one and we will go to the next. So as you can see here, we are plotting, and after that, we will just try to simplify our problem by selecting the first two classes. So in this line here, yes, in this line here, we selected the input features. I will call it X. So I will select the first 100 points. Why is the first 100 points? Because the first 100 points corresponds to two classes, and we need to use a perceptron. And if we need to use a perceptron, we need to convert our problem into a binary classification problem. How many features? I will use the third and the fourth features, which corresponds to petal length and petal width. Why 2? Because I want to plot this data in two-dimensional space. You can select 3, in fact, or 4. But when it is 3, you need to plot it in three-dimensional space. When it is 4, it will be difficult to plot it in one graph. Y, which will be the labels, it will be the first labels of the first 100 points, because the first 100 points corresponds to two classes, class 0 and the class. So as you can see here, we will do also some standardization. I mean standardization because just forget about this one, but standardization, it's a data pre-processing technique, which we use to convert all features into features with a 0 mean and standard deviation of 1. With this one, all X value here will have 0 mean, so the mu equals 0 and the sigma equal 1. If you want, I mean, it will help the model a little bit. So after doing this standardization, you will have the input features will be like this one. So it will be like this one. So this is the original. Those are the original features. Those are the numbers, right? And when you do standardization, it will look like this one. It will be converted into this one. But just don't worry about that. This process, it's like data pre-processing. We call this one data pre-processing. Data pre-processing. It will help the model. So we can do standardization or normalization. Normalization means we will normalize all values. So all values should take a value between 0 and 1. So minimum 0 and maximum 1. Even if those numbers are really large number. I mean, we do this because we need to be sure that all numbers are within the same range. Because imagine that you are classifying a problem and one feature, one input has a value in millions and the other one in hundreds, for example. So maybe the model will try to overestimate large values. So we try to help the model. We try to prevent this by normalizing all values. So all large values will be a number between 0 and 1, and all small values will have a value also between 0 and 1, which means all input values will be treated equally. Yes. So now we did that. We selected X, and X now equals the first 100 points, and we selected two features, petal length and petal width. And the labels also, it will be the labels of the first 100 data points, which corresponds to only two classes. The first class is 0 and 1 class. Now we need to build a model. So I will use a perceptron, correct? So I need to plot my model. So my model will look like this one. We will have a perceptron, and this perceptron will have two inputs. I will call it X3 and X4, X3 and X4. This one will be or just x1 and x2, for example. This one connect by omega1, omega2, correct? We will take here the weighted sum, and after that we will apply it to an activation function. Remember, we did that last time. And this is the output. Y, for example, it's prediction. And also remember that we have something here called bias, right? So, so the perceptron will have two inputs. As you can see here, I defined my perceptron. So model equal perceptron. We need to define here number of iterations. So we will train this model 400 times, 400 iterations. And we have here something called eta. This eta, it's the initial learning rate. This one, it's learning rate. And random state here called 0 or called 1 or called 42, for example. It's just a way for to be able to reproduce the same results. So now we selected a model. We call it a model. And now we will train this model using x and y. So the input to this model will be x. Do you see? So x, in fact, it's equal this x3 and x4. And y is the output labels, correct? So we will train the model using this function called fit. And after this step completes, we will use this model for making a prediction. So I can calculate prediction using model.predict. So when the input is x, we should get y predict. If the model works fine, we should get y equal y predict. So if the accuracy of your model is 100%, so in this case, we should get y predict equal y. So the prediction equal target values. If you want to get the model parameters, we have those model parameters. It will be coefficient, which is omega1 and omega2, and the intercept. This intercept, it's the bias. This model has 3 parameters: omega1, omega2, and b. If you want to print it out, you need to print model.coefficient and model.intercept. So in this case, you will get omega1 from this command. You will get omega1 and omega2, and from this one you will get b, which is the bias. So when we did printing, we got here. I mean, we got here this coefficient. We have the first number here and the second number. So in fact, the first number corresponds to omega1, and the second number corresponds to omega2. Correct? And also, when you print model.intercept, you will get this number, which is almost 0, for example. So B means the bias equal 0. After training your model and testing it, because we tested it using X, remember that we trained the model using X and we tested it using X, which is not correct, but we just make it simple. So if you want to calculate model accuracy, you need to subtract y from y predict. Y minus y predict. If y minus y predict equals 0, if the summation of y minus y predict equals 0, what does this mean? I mean, y minus y predict, this is the error. And if the summation of this error equals 0, it means my model has perfect performance. So the accuracy of my model is 100%. So we need to calculate prediction error. Prediction error will be the summation of y minus y predict squared. Why we square it? Because if you didn't square it, you will get some negative and positive. So imagine that y minus y predict, sometimes it will be -1, 0, +1. In this case, if we will take the summation will be 0 because negative values will cancel positive values. So you will get an error equal 0, which is not correct because you have some -1 and some +1. -1 means I predicted this one as 0. I mean, this class was 0, but the actual class was -1. In fact, it was 1. So it will be 0 minus 1. Or it was 1 and it was predicted as 0. So it will be 1 minus 0. So sometimes you will get positive values. Sometimes you will get negative values. Sometimes you will get 0 values. So to be sure that negative values will not cancel positive values and it will be counted, we need to square this part. We need to square the error. We call it mean square error, right? So we need to square it. So when you square it, you will calculate the summation of each instance where there is error, right? So if your model performs, so for example, if you got this number equal 0.95, right? So it will be or 95% accuracy, for example, accurate. So it means that there are 5 cases where y is not equal to y predict. So it's very important to square this error. Very, very important. Otherwise, you will get misleading values, because maybe negative values will cancel positive values. You will get a nice number, which is 0, but this is not reflecting the reality. Maybe the model is not good as it is seen from this. So to avoid this problem, we need to square y minus y predict. And after calculating it, we need to divide it by n, number of my data points. So we need to multiply it by 1 minus 1 divided by n. So in this case, in programming, you can just calculate the mean value of squared error, So you will get the prediction error. And as you can see here, this prediction error equals 0, which means your accuracy is 100%. So your model is able to classify each single example correctly. So after doing this, we have omega 1 and omega 2. And this is my model. As you can see here, this is my model. So now we need to plot my decision line. We want to plot our decision line. So if we need to plot the decision line, we need to go down. Okay, so now we need to plot the decision line, as you can see here. So I will plot my model one more time. Yes, I will just plot my model. So my model will look like this one. So again, this is my perceptron, and my perceptron has 2 inputs. One input called beta length and beta width. So this one beta length and beta width. So I will call it x1 and x2. This one is connected by omega 1, omega 2, and we have here something we call it bias. We will take weighted sum, and after that we will apply it to my function, my activation function, step function, right? Y predict. So this one we call it step function. So in fact, we calculated a value here. We call it net. So net equal omega x plus b, or omega 1 x1 plus omega 2 x2 plus b. So this is my decision line. If we can set this value equal 0, this one will be my decision line, right? So we need to plot this line. So first, let us plot my classes. We have class 0 and class 1, right? So I will plot the first 50 points. And I will color it, give it color red, for example, and I will call it label 0. So we have this one class. We have here another class. We need to plot this line. So I told you the equation of this line, it will be omega 1 x1 plus omega 2 x2 plus b equals 0, right? All data points which are located above the line, it will be classified into +1. And all data points which are below the line, it will be classified into 0, correct? How can we plot this line? It's simple. I mean, you have the value of omega 1, you have the value of omega 2, you have the value of b. So we just need to assume some values for x1. So if we can assume a value for x1, yes. So I just need to, if x1, as you can see, if you look into here this graph, I mean, x value, its number may be between -2 and 2, for example, as you can see here. So its number between maybe -2 and +2. So we just need to generate values for x1, right? And to substitute those values into this equation to get values for x2. So if I have values for x1, I will write the equation of x2. So x2 will be minus omega 1 x1 minus b divided by omega 2. So just if you have any values for x1, substitute those values into this equation to get x2, and after that plot x1 against x2. So now, as you can see here, I used this command for generating values from x0 minimum to x0 maximum using this step. So now I generated all values for x1, and I will substitute those values into this equation. Remember, model coefficient, this one, it's model dot coefficient 0, right? And this one, it's model dot coefficient 1, right? And this one, it's intercept, it's model dot intercept, it's model dot intercept. So as you can see here in this equation, all this equation, it's just this one. It's equation for x2. So it will be x2 equal minus omega 1 x1 minus p divide all by omega 2. That is it. So once you have x1 and x2, you can just plot x1 against x2 using a green dash. So it will be green line. So in this case, we can plot this decision line. So in fact, this decision line has been generated using this model, right? This is our model which generated this decision line. We call it decision line. So it is decision line because this line will try to separate those two classes into class 1 and the class 0. So now this is my model. If you want to test this model in the future, for example, if you have a new data point in the future, new species, someone he went to the farm and he tried to measure this petal length and the petal width, he got a point. He will just imagine that he got a point which is, for example, 0.5 and 2, for example, a point which is here. Do you see this point? Imagine that we got a species in the future which has a petal length of 0.5 and the petal width was 2 centimeters. We will get this 2 points. We will put it in this graph, for example, and if those 2 points are above the line, in this case, it will be classified as Setosa. Otherwise, it will be classified as versicolor. That is it. So in fact, our model, it's this decision line. Our model is this line. We build this model to get this decision line, and we will use this decision line for solving similar problems in the future. So this is one way for plotting this decision line, which is very simple. There is also another way, and this other way, in fact, is to use mesh grid. Use mesh grid, and in this mesh grid, it's also simple. So you need to generate values. If we have this, I will explain it here in three-dimensional space, for example, right? So so it will be like this. This is my data points. This is x1, and this is x2. So I will generate values for x1, all those values, using a step equal 0.1, for example. So I will try to plot a grid like this one. I will get all those data points for x1. Those data points from here, all those data points. And I will do the same for x2, so I will get those points. I like this approach because it's much simpler, especially when we are working with more complex model. So we will get values for x2. So I got x1 and x2, and after that I will use one command called mesh grid from NP. The input to this mesh grid will be x1 and x2, and the output will be the grid x grid 1 and x grid 2. Once you have x grid 1 and x grid 2, it will be the coordinates of those points. So xg1 and xg2, it will be those coordinates, right? So I will have the coordinates of all those points. So what will happen is that I have my model, correct? I have my model. So I will send those points to my model to predict its classes. So I will send the whole set of points, xg1 and xg2, to my model as an input. to predict Z. Once you have Z, you can use contour plot for plotting XG1 against XG2 against Z, for example. So in this case, you will get all those data points classified. So first we got all X1 values with good resolution, 0.1 step, for example. And I did the same for X2. And I used a mesh grid function for generating those coordinates of the grid, XG1 and XG2. And after that, I will send all those data points, all the grid values, to my model for prediction. So remember, we had last time the line was like this, correct? So in this case, all data points which are above the line, it will be classified as class 1, and all data points below the line will be classified as class 0. So we will get that and we will plot it. So it will look like this one. You see? So now we have the decision line and all data points which above the line, it will be all data points, because this is grid points. It's not only your data set, but all data points, all the grid values which are above the line, it will be classified into +1. Right? All data points will be classified into +1, all those grid points, and all data points which are below the line, it will be classified into 0. So it's very easy for doing it. So please, if there is something difficult, please just ask me immediately. So, but we did something wrong here, as I told you from the beginning, because from the beginning we didn't split our data, as you can remember. So we have X values here, as you can see here, we have those X values, right? We have those X values and Y values. And we used the whole X values for training my model, right? As you can see here, we used the whole X value for training my model. As you can see here, we used the whole X value and the whole Y value for training the model and for making a prediction for testing. So this one, in fact, this step, we call it training. And this one, in fact, for prediction, we call it testing. So in fact, we have been training and testing the model using the same X value. This is not correct. Because if you need to train your model, you need to train the model using a training set. And after that, you need to hold out part from the data for testing. So in this case, we can test the model using new data. You cannot test the model using the same data, because I mean, we did that last time, and as you can see, we got an accuracy of 0%. Sorry, the prediction error was 0%, which means accuracy was 100%. In fact, it's 100% because we trained the model using X and we tested the model using X. It's like you have an exam, for example. So I will give you 5 questions to study at home, and we will use those 5 questions in the classroom. And after that, you will get the same 5 questions in the final exam. So it is expected that he will get 100%. But in reality, we should split our questions. We need to use some questions for studying at home and in lectures. And at the end, in the exam, we need to get a new set of questions to be sure that all people will be evaluated fairly, right? So this is a big mistake which we did. But we did that because we need to make it simple for us. So now we need to do it correctly. If you want to do it correctly, we need to split our data, right? We need to split. So we have very nice function. We have very nice function called train test split. You see this function? It's called the train test split. So before doing anything, you need to split your data into one part for training, one part for testing. You will use the test as a training part for training your model and the test part for testing your model. In this case, you will get good results. And the people will trust your work. Otherwise, people will not be able to trust your work because the model has been tested and trained using the same set, which is not correct. So we have this nice function, and this nice function, we need to import it from sklearn.model selection. We have from sklearn.model selection, we need to import this function which is called the train test split. The input to this function will be the whole x, the whole y, and also maybe the test size. What is the test set size? Maybe test size equal 0.3, which means this one means 70% of the data will be used for training, and 30% will be used for testing. So because this test size ratio is 0.3, you can change it. You can make it 0.2. When it is 0.2, it means 80% will be used for training and 20% will be used for testing. And this function, in fact, it shuffles the data. So you can use here random state equal 1 or random state equal 42. This is random seed. This one is very important for reproducibility. Because if I didn't use this command here, each time we will shuffle the data, we will get different training and different testing sets. If you want to get each time the same training set and the testing set, you need to use this random state equal, for example, 42. And in this case, we will be able to reproduce our results because this function train test split, it shuffles the data. It will shuffle it. If you want to get the same set each time, you need to use random state equal something. You need to use random seed here to be able to get the same examples in the test and the same examples in the training set. So as you can see here, the output from this function will be x train, x test, y train, y test. I mean x, it's the inputs, input features, y is labels. So the input features will be split. So x will be split into x train and x test according to this ratio. And also y will be split into y train and y test according to the same ratio. So now I can use x train and y train for training my model. And I can use x test and y test for testing my model. So now my results will be more better, because the model will be tested with brand new data. This is very important. If I need to test my model, I need to test my model with a brand new data. We call this technique, in fact, hold out validation. I mean, this technique, we call it hold out validation, which means I will hold out part of the data for validating my model. Very, very famous technique. So if you want to print, for example, y test, just to show you y test, now it will be like 0, 1, zeros, 1, zeros. And the size of this one will be 30% of the total, right? Remember that we used 100 data points, 100 data points. 30% will be 30 data points. So this one should be 30. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this one, in fact, is 30 points. Why it's 30 points? Because we selected test size ratio equal 0.3. And the total size of my data set was 100. So which means 30 points will be used for testing and 70 points will be used for training. We will split it. Remember that we have two classes here because we solve the problem as a binary classification problem. So if you want to see how many labels in each class, you can use a command called bin count. You can get bin count of y train and the bin count for y test. When we do bin count for y train, you will get this number, 36 and 34, which means 36 of class 0, 34 from class 1. When you do it for y test, you will get this number, 14 and 16, for example, which means 14 from class 0 and 16 from class 1. Which means in the training set, we have more from class 0. It's 36 and 34. So from class 0, we have 36 examples. From class 1, we have 34 examples. In the y test, it's 14 from class 0 and 16 from class 2, right? So it's not equally represented, correct? Not balanced. If you want to make it balanced, which is highly recommended, we need to add something here, another command here in this train test split, another input which is called stratify equal y. When you use stratify equal y, you will get exactly the same number of classes in each set, right? So it will be like this one. You see? So now it will be 35, it will be equally as much as possible. So it will be 35, 35, right? It will be 35, 35 from, so now it's equally, and the 15 and 15. We got this when we use the stratify equal y. Stratify equal y is very important. When you select stratify equal y, it will try to stratify labels. So both classes or the three classes or whatever, it will be equally represented in the training and testing set, which is much better for fair performance. Because if you didn't do this, what will happen? In the training data, in fact, we have more from class 0 and less from class 1. So we should expect that this model will be more clever in classifying a class 0 compared to class 1. And in the test set, we have more from class 2 compared to class 1. So in fact, the test set will be the opposite. That model will be tested with more from class 1 compared to class 0, for example. So should expect that the performance here will not be very good because I trained the model for more from class 0 and I will be tested it for more from class 1, right? So to avoid those complications, you can just select stratify equal y. Remember to use stratify equal y. When we use stratify equal y, we will try to be sure that the two classes are equally represented. Okay, so now we will repeat our training process. So we'll clean, and we will try to repeat our training process using X-train and Y-train. We will do it correctly, right? So now I have the same model. It's a perceptron. We selected maximum number of iterations, 10 iterations. It has the same value. Validation fraction, this is also something very important. This validation fraction, I will talk about it later on. But just this validation fraction, in fact, it's when we are splitting my data into training and testing, you remember that my data was like this one. I have 100 examples, and I will split into one part for training. That part will be used for training. And that part will be used for testing. So it's fine, but also, in fact, we can try to get another part from the training set. We call it validation set. We can split the training part one more time, this training part. We can split the training part here one more time and try to get here a small part of it, like 10% of it, will be used for validation. It will be used for validation, and this is something useful for to discover if my model has overfitting or not. We will talk about it later on, but you can just forget about it. But if you are asking what is the meaning of validation fraction, equal 0.1, for example, it means 10% of the training data will be used for validation. And we used here random state equal 42, and it's because my model, when we have a model like this one, which has two inputs, x1 and x2, and have a bias, we initialize those omega 1 and omega 2, correct? So we will initialize those omega 1 and omega 2 and b by random values. So if you want to reproduce your results, you need to select random state equal 42. When it's random state equal 42, if you will run this model 20 times, each time you will have the same random sets, random values for omega 1, omega 2, and b. So it should be possible for people to reproduce, get the same results. So if I didn't use this one here, in fact, maybe I will run it this time, I will get some results. Maybe accuracy will be 97%. And if I will run it another time, maybe I will get different one, which is 92%, right? Why? Because the model has been trained using the same approach, the same data, but the difference here, without using random state equal 42, we will initialize those parameters with different values each time. So now we will train the model. We will train the model using X-train, Y-train, not using X and Y as we did last time, but now using the training data set. And after that, we will print the model coefficient and the model intercept. you can calculate the training error. So it will be the mean value of mean squared error. So it will be y train minus model predict x train. And you can did that also for the test set. Now we are testing. This one's the test error, training error. This one's the test set. When it's a training error, you need to subtract y train from y predict for x train. When it is test error, it will be y test minus prediction for x test. So this one, it's testing error, for example. We will train the model. Okay, we will train the model, and after that we will calculate the test error. And as you can see here, we have here 2 zeros, right? So the first one, it's the training error, and the second one, in fact, it's testing error. Right? So in fact, this technique, we call it, the technique which we just did, we call it holdout validation. We call it holdout validation. I mean, in this code here, we have another part which called the cross validation. I don't want to talk about it maybe now because it will make you confused, but also another technique. We have two techniques, holdout validation and cross validation. But it's just simple. I will just talk about the code here, but later on I will explain it. This is cross validation. It is the same function from sklearn.model selection. We need to import cross validation score. And the cross validation score, in fact, it's instead of dividing my data into one part for training and one part for testing, we will divide it into k-folds. We call it k-fold cross validation. So this technique, we call it k-fold cross validation. And in this technique, instead of dividing my data into one part for training and one part for testing, we divide our data into number of folds or blocks. So this data will be divided into one. For example, if we selected k equal 5, so it will be divided like this one. 5 blocks, 5 equal blocks, right? And what will happen here? We will train the model using k-1 folds. So for example, first I will train the model using this one, and this one, this one, and this one. It will be trained using this one, and it will be tested. It will be tested using this one. So I will train the model using a k-1 folds, and it will be tested with the other one, with the rest. And I will repeat this process k times. So next time, I will train the model using maybe this one, this one, this one, and this one. And it will be tested using this one. And I will calculate the accuracy. And I will repeat this process k times, right? So when it is k times, it will be like training the model using this one, this one, this one, and this one, and it will be tested using this one. So in this case, we will get 5 or k error values, k accuracies or k scores. We will take the average, and this average will be the average score of my model. And after that, I will go back again. I will use my model again, and I will train it using the whole data set. So in this case, it has some advantage compared to k-fold cross holdout validation, because in holdout validation, we split the data into 2 containers, one for training and we hold out one for testing. But in case of k-fold cross validation, you don't need to hold out any data for testing. You just need to divide your data into k-folds, and you will train your model using k-1 and test it with number k. Repeat this process k times. Each time you will get a score. And at the end, you will take the average of this score. It will be the average of your model, the average score of your model. And after that, you will test your model using the whole X and the whole Y. So in this case, we should expect that your model will have better performance because your model will be subjected to more data in the training process. And as you can see here, we got mean accuracy equal 1, which is 100%, standard deviation equal 0, and these are the model parameters. This is omega 1, this is omega 2, and this is bias. So now we can plot the decision line. So this technique, it's a hold out validation or cross validation. We will talk later on about it because we will use it many times. So please, do you have any questions for this example? Any questions? Okay, so we will go to our slides one more time. So as you can see, we did this implementation, right? So in this example, in fact, we studied hold out validations, the cross validation. We studied how can we plot the decision line using two approaches, correct? Yeah, so this is how can we plot the decision. It's just an explanation now. So this is the implementation using sklearn. We can plot the decision line using as a line. As you can see, this line will divide my search space into two sections where one class will be located above, one will be located below. The one which is located above, it will be classified into, for example, +1, and the one below it will be classified into 0, right? If you want to plot the decision line using mesh grid, we learned how to do it, right? I like this approach. In fact, it's much better because we don't need to worry about the equation, because maybe your model is very complex and it's very difficult to find this equation. If it is straightforward in neural network, it will be impossible to get this equation. We can get this equation only for a perceptron, but when it is straightforward in neural network, it will be complex. So I recommend you to follow this approach. This is splitting the data into training and testing sets. We explained it. We call it hold out validation. So this is my data. We will split it into two parts, one for training. One part for training could be 70%, and the 30% will be used for testing. Correct? So we call this technique, it's hold out validation. Hold out validation. But also there is another technique which is called k-fold cross validation. This one we call it k-fold cross validation, and if you select k equal 5, it will be like this one. So we will divide my data into k folds, 5 folds, for example. So and each time I will use 4 for training and 1 fold for testing. Correct? And the k, it's a hyperparameter. You can select k as much as you want. You can select k equal 10, no problem. If you select k equal 10, it will take 10 iterations. Correct? You need to repeat this one 10 times. If k equal 5, so I need to repeat this one 5 times. So if you select k equal 20, you need to repeat this process 20 times. So it will just take more time in the training process. And each time you will get a score, and at the end you will get the average score. This average score will be the average accuracy of your model. And after that, you will train your model using the whole data set. So it's much better compared to hold out, because in hold out, we hold out that part for testing. We will not be able to use this one for training. But in case of k-fold cross validation, we can use the whole data for training after testing model accuracy. So this is hold out validation versus cross validation, correct? And also there is something called the k-fold versus stratified k-fold, because also stratified k-fold is very important, because we want to be sure that all classes will be equally represented in those folds. Very, very important. So we can use k-fold cross validation, and we can use something called stratified k-fold. When it is a stratified k-fold, we will be sure that all classes are equally represented in those k-folds. So stratified k-fold cross validation is variation of k-fold that return stratified folds. we need to be sure that all the folds are stratified, which means all classes are equally represented in those folds. Folds are made by preserving the percentage of samples for each class. If shuffle equal true, it shuffles each class sample before splitting into batches. Yes, maybe we can talk about this, but it's just, I mean, when we use a stratified k-fold, I mean, in this example here, you need to import it from sklearn.model selection, cross-validation, k-fold, and a stratified k-fold, as you can see. And I have here a model. My model is perceptron, as we did before. And I will use k-fold. Correct? When you use a function called the k-fold, the input to this function will be number of splits, number of k, for example, and random state, and the shuffle equal true. So each time it will be shuffle. When it split each time, it will shuffle. So in this case, I will split my data into k-fold, and I will train my model using each k-1 and the k. When you use a stratified k-fold, it will be the same, but you will use a stratified k-fold. And in this case, you just have the advantage that your folds will be stratified, which means all classes are equally represented in each fold, right? So it's very important. So if you have imbalanced data sets, for example, and if you want to be sure that your model will perform perfect, it's highly recommended to use stratified k-fold. Very, very highly recommended. So as you can see here, I will use k-fold. This is k-fold. This one, it's a stratified k-fold. Do you see the difference? Well, it is only k-fold. This is a number of class 0 and the class 1 in the training, a number of class 0 and the class 1 in the test. They are not equally represented, correct? Do you see those numbers? For example, do you look into, can you see this one? So this model will be tested using 5 from class 0 and 15 from class 1, which is not good. But if it will be stratified, you can see that all classes are equally represented, exactly the same. 40 from class 0, 40 from class 1, 10 from class 0, and 10 from class 0 and class 1. So this one is very, very important. So if you want to be sure that your model will perform well, and you are sure that all classes are equally represented, so in this case, instead of using a k-fold, you need to use a stratified k-fold. Okay, so next part, we will talk about linear models for multi-class classification, but we will take a break now we need to start again at yeah, so we will stop here now and we will start again after maybe 15 minutes or 20 minutes. So the next part of lecture and lab. So you can work with some examples, or we can work with this multi-class classification, and after that you can work with some examples in the next part. So thank you very much. If you have any questions, please don't hesitate to ask me.